Welcome to the Picture Language Seminar. We're really happy today to have Jordan Cotler. He's been a student at MIT and at Stanford, now is a member of the Society of Fellows at Harvard. He's an expert on entanglement, OTOX, and today we're going to hear about quantum enhanced learning. So Jordan, we're looking forward very much to your talk.
Great. Well, thank you so much for giving me the opportunity to speak, and it's nice to finally be around Harvard in person. And of course, if you're in town, if you're in Cambridge, feel free to send me an email. It'd be great to further discuss any of the things I'm about to tell you in person. So let me share my screen. Let's do this. Okay, can everybody see? Looks good?
Looks good.
Fantastic. And feel free, of course, for anyone to ask questions throughout the talk. So I'm going to tell you about some recent work, both forthcoming work and work over the last year, which is joint work with Sitan Chen, Robert Huang, and Jerry Lee. And the subject is quantum enhanced learning using a quantum memory. And I'll explain in turn what that means. So let me begin by asking a question, which is, what is an experiment? Now, there are many different kinds of protocols which fall under the purview of experiment that are actually very different from one another. So maybe it would be useful to list some of them to show how varied the notion of experiment is and why it's not actually obvious what is an experiment. So this could include, for instance, measuring constants of nature, such as the speed of light or the charge of an electron. It could be quantifying dynamical properties, such as the rate of a chemical reaction, or inferring structural properties such as the symmetry group of a crystal, or learning more abstract information such as the chain of chemical reactions that comprise photosynthesis, or whether Yang-Mills describes the strong force. So this really emphasizes the question, what exactly is an experiment in its full scope of generality? Now, the reason why we're going to be interested in this question is that we would like to frame an experiment in the language of quantum information theory and quantum computer science. In particular, we would like to think of an experiment as a type of protocol or a type of algorithm so that we can bring to bear the tools of computational complexity theory to ask questions like, what is the computational complexity of an experiment? Are there certain experiments such that if you had the resources of a quantum computer available versus if you did not, such as in contemporary experiments, would that confer any advantage to having the quantum computer in terms of the resources required to perform the experiment? So there have been some recent perspectives in the direction of recasting experiments in the language of quantum information. Let me give two of them that have were both in papers in the last year, which is that the perspective of Huang, Kung, and Preskel, which is that many experiments can be thought of as quantum learning algorithms, which learn properties of partially uncharacterized systems via examples. So this is a kind of compelling intuition that when we have a learning protocol, we are given data, which we make measurements on, we learn information about, and then we use whatever we have learned from previous data to inform how we are going to then measure and manipulate and further learn information from new data that we are given thereafter. So there's an adaptive protocol of learning about nature via interaction. That's their perspective at a high level. A very related perspective, which came out in a paper around the same time with Dorita Hironoff, myself, and Xiaoliang Xi, is that all experiments are examples of a framework we call quantum algorithmic measurements, abbreviated as QALMs, which are a hybrid of black box algorithms and interactive protocols. Now, these ideas were also based off of previous frameworks in the last 15 years. But I'll be particularly concrete about the kinds of experiments that we're going to discuss here. So I'll outline in a very precise way what it is that we're going to talk about. We're going to be interested in quantifying the power of a quantum memory and helping us learn about nature via experiments. Roughly speaking, we're asking the question, if you have an experimentalist who has a quantum computer in their lab that they can couple to their experimental samples, does this help them perform certain kinds of experiments much more efficiently than they would otherwise be able to do? Now, we're going to consider two kinds of experimental protocols, which I will detail. One which we say are those with a classical memory and those with a quantum memory. These will roughly correspond, the former, the classical memory case, will roughly correspond to experiments which model what contemporary experiments, and maybe experiments, say, in 20th century physics, were able to do, in which you have a quantum system, you're able to make measurements on it, and you store the data as classical data, and you can use that classical data to inform future measurements that you make and how you then analyze that future data. And we're going to contrast that with a new setting in which we can really couple our experimental samples to a quantum memory, and more generally a quantum computer, so that we can store quantum data and manipulate that quantum data with the full power of quantum computation. So let me explain what I mean by protocols with a classical memory. So here's a flowchart of different subsystems that we can imagine having for the experiment. One is the nature subsystem, which we can imagine is the sample. Here's graphene, for example. It is the sample from nature which we wish to interrogate, that we wish to learn about via our experimental protocol. We also have the lab subsystem, which comprises the experimental apparatus that we are going to use to directly interact with nature. Finally, we have the classical memory, which we can think of as a classical computer, which can interface in a classical manner with our experimental apparatus. It can inform it can tell the experimental apparatus what to do. Namely, it can inform it how it should interface with the experimental sample. It can also store classical data. If we have outcomes of measurements in the lab system, they can then be stored on the classical computer. And then that information that's stored on the classical computer can then be used to determine how we should reconfigure the lab equipment to make future measurements, and also how we analyze future data that is procured by the apparatus in the lab. So what is a protocol? An experimental protocol, at least of the simple kind that we'll discuss in this talk, proceeds in T different rounds in which nature is queried once per round, namely the lab and nature interact once per round. That defines what a round is. So in each round, we first prepare a state on the lab system, which can depend on the classical memory. In other words, we have some initial configuration of the lab system to begin with. Then what we do is we query nature. We induce an interaction, a quantum interaction between nature and the lab. So this interaction essentially couples the two systems together. Then what we do is we measure the lab system here with the POVM. You can just imagine that we make some kind of measurement on the lab system if we want to be slightly less technical about it. And then we store the classical outcome of that measurement of the lab system in the classical memory. And then what we do is that we reinitialize the lab system and we repeat the procedure. So the procedure proceeds as follows. We initialize the lab system, we couple nature in the lab, we make a measurement on the degrees of freedom in the lab, and we store the classical information of that measurement outcome in the classical memory. And then this procedure is repeated potentially adaptively, namely that the kinds of interactions between nature and the lab can be determined by the outcomes of previous measurements. And moreover, the kinds of measurements we make to determine the classical data from the configuration of the lab once nature and lab have been coupled, that measurement that we make can also depend on the configuration of our classical memory. Now let me contrast this with the setting of quantum memory. In the setting of a quantum memory, well, these systems play the same roles, except that now we might have access to a full-fledged quantum computer instead of just a classical computer, in which we can store quantum states and we can have quantum interactions between the lab apparatus and the quantum computer. Quantum information can go back and forth between them. So essentially, the protocols look quite similar, except that they now have additional capabilities that we can prepare a state on the lab system, which can depend adaptively on the quantum states which are stored in the quantum memory or in the quantum computer. We then query nature, where nature and the lab then interact with one another. And then we can measure the lab system and store the resulting quantum state on the quantum memory. So in other words, we don't just need to store classical information about the outcome of the measurements. We can actually store the quantum state itself, which which come from the measurement outcomes on the lab.
Sorry, just a question about that. If you're making a measurement like a POVM, then aren't you like collapsing the wave function to some degree and therefore getting a classical outcome as a result? So what do you mean by you're storing the quantum outcome if you're applying a POVM?
Yeah, so in the classical case, what we allow ourselves to do is to store so suppose that we have a POVM which has n outcomes. The information that you're storing is the index, just the classical index. Whereas I'm saying, well, more generally, you could actually store the state that you get instead of just the index of the outcome. Is that?
Is the state a probability distribution on like the, let's say, eigenvectors describing the POVM, or is it you're actually storing the density matrix before you apply the POVM?
So what I mean is that we collapse the wave function via the Born rule, and you get some state probabilistically, and we store that state.
Got it. Okay, thank you.
Sure. You could also think about it as storing a density, but yes, let's think about it in the way that I said, where you store the state after collapse and use the Born rule. So in any case, we would like to find tasks for which there is an exponential advantage using a quantum memory versus using a classical memory. And there are two parts to this endeavor. The first is to show that a task can be done efficiently if we have access to a quantum memory, which is to say that if we have access to this quantum computer with the manner of coupling which I described, then there is an efficient protocol to do some particular task. Now, the other thing is more challenging, which is that we would like to show that a task is exponentially hard if we only have access to a classical memory. So this first part is easy. All you have to do, if I give you a task, is to exhibit one efficient protocol that uses the quantum memory, show that there is an efficient way of doing it. But the second part is, this is the technically challenging part. It's because if you would like to show that a task is exponentially hard if we only have access to a classical memory, you have to rule out all efficient protocols. And this is the main technical challenge, is to rule out all efficient protocols that you can do in the setting of a classical memory. And this is what we're going to develop technology to do in this talk. And most of the results are going to be consequences of this new technical apparatus that I will introduce, which allows us to prove these kinds of exponential separations. So there's been a lot of recent work in this direction. In particular, there has been exponential separations in gate and query complexity for learning properties of classical oracles in some contexts of some interesting but maybe slightly contrived problems like the generalized versions of Simon's problem or the welded tree problem. There have been exponential separations in query complexity for learning Pauli observables in this paper I mentioned before by Huang, Kung, and Preskel from earlier this year, as well as exponential separations in gate and query complexity for learning properties of quantum states and channels in this paper with Aharonov, myself, and Shi. But in the work that I'm going to tell you about today, we're going to synthesize and generalize the approaches of three recent papers. A paper on mixedness testing by Bubeck, Chen, and Li from 2020. This paper I mentioned by Huang, Kung, and Preskel from this year, as well as this paper by Dorit, myself, and Xiao Yang. And we're going to provide a new framework for proving exponential lower bounds for protocols with classical memories. And as I mentioned, this will allow us to prove new exponential complexity separations between interactive protocols with and without quantum memories. So let's get to the first example to orient us. This will be the simplest example, but it will demonstrate the key ideas in the framework. So let me first tell you what the results are and sketch what it is that we can prove, and then I will sketch how the proof works for this particular kind of problem. So suppose I give you the following task. You should distinguish between, on the one hand, the maximally mixed state, and on the other hand, a fixed Haar random pure state. So imagine this. Imagine that you have a nature system, and when you couple to nature, nature provides you with a quantum state. That it is a quantum source, which when you query nature, it provides you with a quantum state. And either every time you query nature, you are provided with the maximally mixed state on n qubits, or every time you query it, you are provided with a fixed but Haar random pure state. Namely, there is a Haar random pure state, namely a state that is chosen uniformly at random over normalized n-qubit states, which is chosen at the outset. And when you query nature, you are given a copy of that state every single time you query nature. So you would like to determine if the state that nature is providing you with is always the maximally mixed state or always this pure state. So this is a purity testing problem. So, okay, so the basic question that we want to answer is, if you would like to distinguish between these two possibilities, how many states do you need to be provided with in order to do so? Do you need just a few states to be able to tell the difference between these two scenarios? Do you need many, many states? How does that scale with the number of qubits? So a result from this paper with Dorit and Xiaoyang is that if you have access to a quantum memory, you can essentially do a swap test, or not essentially, you can do a swap test, which just requires essentially just a few queries that doesn't scale with n. But the interesting result is that if you would like to distinguish between these two possibilities only with access to a classical memory, even if you work adaptively, you require a lower bound of exponentially measurements in n to distinguish between these two different cases. And so this complexity, by the way, for those who is in the sense of query complexity, it's the number of states that you need, that you are querying from nature, the number of copies. So I'd like to make a comment that in this paper with Dorit and Xiaoyang, the proof of this classical lower bound, which is the technical meat of the proof, is about 20 pages long. It's a somewhat elaborate proof. But in this new framework that I'm going to tell you about, that from a forthcoming paper.
Can I interrupt you for a second?
Yes, absolutely.
Now, do you take into account the complexity of storing the quantum state itself? So storing the classical state has one complexity, storing the quantum state has a different complexity. So does that get counted here?
Yeah, so let me make a comment about that. So in this particular case, so one could ask, instead of just thinking about query complexity, only the number of states which we are asking for, we could ask that the protocol in the quantum case be gate efficient, namely that the operations which we do to store the state and to manipulate it are efficient in terms of that they require a number of gates, which is sub-exponential in that. In fact, the swap test requires essentially order n gates, so it's actually gate efficient. So in other words, the protocol with the quantum memory can in fact be realized efficiently. The one caveat to this, which I'll mention, is that if you wanted to do this particular purity testing task in practice, you would have the problem that you would have to prepare, like the states that we're discussing are these Haar-random pure states are not efficiently preparable. So even though the protocol to distinguish between maximum mixed states and Haar-random pure states is efficient in terms of gate complexity, the preparation of the states itself by a nature system is not actually gate efficient. We'll return to this later and be able to ameliorate that issue with a slightly more sophisticated type of purity testing problem. But the short answer to your question is that the quantum memory protocol can be realized in a gate efficient way.
Thank you.
Sure. So anyway, so this new result is that we can prove something stronger, which is that in the case of the classical memory, we are essentially lower and upper bounded asymptotically by 2 to the n over 2 queries. Namely, the number of states that we require is lower bounded by essentially 2 to the n over 2, but also so you cannot do worse or better than 2 to the n over 2 asymptotically. So this is, in a sense, the query complexity of distinguishing between a maximally mixed state and a fixed Haar-random pure state. But moreover, what's interesting about the proof is, whereas in the previous framework it was 20 pages, the proof of the classical lower bound here is actually a half a page, and I will give you the proof in like 2 slides. So let me tell you what the conceptual framework here is for being able to prove these kinds of exponential lower bounds. And we call this the learning tree framework. And I'm going to, in particular, tell you how it works for learning quantum states. There's a more sophisticated version of the framework that pertains to quantum channels. But here's the essential idea. Suppose we have a physical source, which I've been referring to as nature, which produces a state row whenever we query it. So it's a quantum source which gives you copies of the state row. And we want to learn about that state row in a setting in which we don't have a quantum memory. So what do? So let's consider a more simple case where we think about rank 1 POVMs, or otherwise, let's just think about projective measurements. So we obtain a copy of rho, and we're going to measure it in some basis, BI, some orthonormal basis BI. And suppose that the output is Q, meaning that suppose that after applying the Born rule, that we measure rho to be in the state B sub Q for some fixed index I equals Q. And we're then going to store the value of Q in the classical memory as the classical information pertaining to the measurement outcome. Then what we might do in the next round of the experiment is that we obtain another copy of rho. And now we're going to measure it in another measurement basis, another orthonormal basis, which can be contingent on the previous classical measurement outcome. In other words, we choose a new basis in which to measure, indexed by I, but depending on Q. In other words, we choose a basis which depends on the previous measurement outcome in maybe some adaptive fashion. And suppose then that the outcome of this is R. We can store that in the classical memory. Okay, I'll do one more example just to illustrate the point. Then maybe the next round, we measure using a basis which is contingent on both of the previous measurement outcomes, Q and R. So B sub QR, and I is the index which indexes the orthonormal basis. And then we can have an output S and store that in the classical memory and so on and so forth. So the idea is that in the learning tree framework, we can think about measurement outcomes in the future as being contingent, or rather the measurement bases that we're using in the future as being contingent upon those in the past. And there's a nice way of visualizing this, namely as a type of tree. So imagine here that we have a tree where each of the vertices of the tree, say in the first level of the tree, corresponds to the basis elements in the initial measurement that you're going to make in the first round. So this is B1 through B and naught. Suppose that and naught is the number of is the dimension. So now suppose that we measure rho to be in the state B2. Then contingent on B2, we're then going to measure it in a basis B21, B22, and so on. And we can think about a particular instantiation of the protocol is being a path through the tree. So for instance, suppose in the first round we measure B2, in the second round we measure B21, we can think about the protocol as instantiating a particular path through the tree, which tells us the sequence of measurement outcomes, which corresponds to the sequence of vertices that we visit when we take a root to leaf path through the tree. So as I said, a particular instantiation of the protocol is a path through the tree, and a tree of depth T corresponds to measuring T copies of the state, because at each level of depth of the tree, we are making one measurement. So this corresponds to one measurement round, this corresponds to a measurement round, and it branches and so on and so forth. So let V naught through VT minus 1 be vertices which label a root, so this is the root, a root to leaf path through the tree. Now, the probability of taking that path, namely the probability that that path is instantiated by when we perform our measurement protocol, is given by this. This is the probability of a particular path through the tree, the set of V's, V naught through VT minus 1. And it's a product of the B's at these vertices interproducted with the state rho. So in particular, suppose, for instance, that we measured rho so consider the path through the tree, just in this simple example, where in the first round, we measure rho to be in the state B1, and in the second round, we measure it to be in the state B1, 1. Well, the probability that we measure it to be in the state 1 would just be B1 rho B1. And the probability that subsequently we would measure it to be in the state B11 would be B11 rho B11. And if we take the product of those two inner products, then we get a product that looks like this. So you can think about this as the probability that we take a particular root to leaf path through the tree. And if we have some other state sigma, for example, that we're being fed instead of the state rho, well, then we can compute what the probability is of a particular path through the tree if instead we were being given a state sigma every time. Now, if we would like to distinguish the two possibilities, if we'd like to know
excuse me, can I have a question?
Yes.
So how deep will you cheat to perform some of the measurements? Like how to determine how deep you can to make a good measurement?
Great. So The answer is that we're going to basically say that if we would like to distinguish, for instance, the maximum mixed state versus this Haar-random pure state, that you cannot do so unless your tree has exponential depth in n. That's what the result is. That's one way of thinking about the result.
Okay, yeah, maybe it's in the next few slides, right? So
I'll get there shortly.
Yeah.
Sure. So in any case, the thing that we want to do, though, is that we have these probability distributions, which tells us the probability of a certain trajectory through the tree contingent on the state that we're being fed. Say either we're given rho each time or we're given sigma each time. And we would like to compare these probability distributions in the one norm, or the total variation distance. And the idea is that if this two probability distributions for rho and sigma, where we sum over pass through the tree, if this quantity is small, it means that our adaptive protocol defined by the tree will have difficulty distinguishing between the state rho and the state sigma, because essentially the probability distribution over outcomes of the experiment, namely trajectories through the tree, will look very, very similar if this one norm distance is very small.
Just a clarification on the second equation for the probability of sigma. The tree you're defining is defined with respect to the state rho. So like all of these eigenvectors are based on your choices. Like if you run this experiment, you choose the B's and your measurements depending on that state rho. But are you using those same vectors for the probability of sigma, or are you redoing the same procedure and those are different B's?
Yeah, so the key point is that the B's do not depend on rho. So think of it this way. The tree is independent of the data of rho. Because what you're saying is this, so the thing that one says is as follows. If you measure B2, we need to decide in advance. Suppose I were to get B2. I mean, what would then be the basis that I would choose thereafter? That's a statement which is not contingent on the state that you're measuring. In other words, the tree is sort of a definition of an adaptive strategy, of an adaptive protocol, which is independent of the states that you're going to be measuring. The states that you're going to be measuring only assign probabilities to potentially instantiations of the protocol, or like how you will traverse different combinations of bases in subsequent rounds. But your choice of bases in advance is your choice of adaptive strategy is prescribed in advance, independent of the state. Okay, great. So there are sort of two proof strategies in being able to show that this quantity is small. One is that you can show that in each round of the experiment, we can try to bound the information the learner can gain by traversing any edge of the tree. On the other hand, there's a path-based strategy, which is we can try to bound the information gain for traversing an entire path, a root to leaf path through the tree. And these different strategies will be useful depending on the context. Okay, so let's go back to our purity testing example, and I'll show you how part of the proof works using the learning tree. So what I'm going to show to you is why, if you only have access to these classical adaptive measurements, you require a lower bound. We'll just do the lower bound version of 2 to the n over 2 measurements, namely a tree of depth 2 to the n over 2 asymptotically, in order to distinguish between a maximally mixed state and a fixed Haar-random pure state. So let me now show you how that works. So let me give you a sketch of the proof of the lower bound. Okay, so as before, let V naught through VT minus 1 be a root to leaf path through the tree. Now, the probability of taking that path for the maximally mixed state, okay, so I just took the formula that I showed you on the previous slides, and I've put in the maximally mixed state on n qubits. What you find is that there is a uniform probability that you take any particular trajectory through the tree, which is 1 over 2 to the n to the power of t, where t is the depth of the tree. On the other hand, if I have a Haar-random pure state, then I should compute this quantity, and we like to average over Haar-random pure states at the outset. And because I don't know, in other words, okay, so anyway, so we have this, so this is the probability for a fixed Haar-random pure state, and then we average over Haar-random pure states because that's chosen initially at random at the beginning of the protocol. And we would like to compare the one norm distance between these two probability distributions over trajectories through the tree. So we like to show that this quantity is small. Okay, so how do we do this? Well, the first thing that we do is we do a little trick to get this absolute value as an annoyance. We would like to get rid of the absolute value. So we do a standard trick that one can do with when you look at the one norm distance between probability distributions. We can replace these absolute values by we can remove them and also remove the factor of half at the cost of only summing over configurations in which in other words, only summing over paths through which P mixed is greater than P pure. You can readily check just by, this basically follows from an identity, which is essentially just that the probability distributions are normalized and implies that this quantity equals this quantity. In any case, let's factor out P mixed. Let's just write this as P mixed times 1 minus P pure over P mixed. If we would like to render this entire quantity small, then we would like for this factor, for instance, to be small. That would be one way of rendering this quantity small, is if this factor is small. Or equivalently, we would like this ratio to be close to 1. If this is close to 1, then this factor is small, which would render the entire sum small. So let's write out what this quantity is. If we just write it out more explicitly using these blue box definitions I've given you here, we can evaluate this expectation value over the Haar ensemble of states. And maybe without going to too many technical details in the interest of time, we can get bounds on this particular quantity, which when you reprocess it through this expression, it shows you that this one norm distance is going to be, it's going to be exponentially small, essentially, unless the depth of the tree is greater than 2 to the n over 2. In other words, the only way of rendering the one norm distance to be order 1, in other words, that the two probability distributions are distinguishable, is only if the depth of the tree is exponential in n. So, in other words, we are getting a condition on the tree depth for which the protocol can distinguish, or for which any protocol that is adaptive and leverages a classical memory can distinguish between the mixed and pure states. So this is a sketch of how the proof works. Okay. So now let me give you some other slightly more sophisticated exponential separations in learning quantum states, which will also be related to some experiments which were done on the Sycamore chip done by Google. So let me tell you about a problem which is polystate property testing. Suppose we're given a quantum state, which is a mixture of the maximally mixed state and basically a Pauli string. So this is our quantum state, identity plus epsilon p, where p is a Pauli string on n qubits. So in other words, it is a tensor product of just ordinary Pauli operators. It's an n-fold tensor product of Pauli operators, say sigma x, sigma y, etc., n of those. And the idea is, given a state of this form, where epsilon is, say, a number between 0 and 1, we would like to determine p. We would like to determine the Pauli string. You can check that this is, in fact, a quantum state that's positive semi-definite. So one thing which is interesting, by the way, is that in the former setting that I gave you for purity testing, there was a problem that if you wanted to realize that protocol in practice, say on a quantum computer in the lab, you would only get the exponential advantage if you could prepare a Haar random pure state, which you couldn't actually do. In other words, the actual protocol of distinguishing between a mixed state and a Haar random pure state, you couldn't really do that in practice because you can't efficiently prepare a Haar random pure state. By contrast, in this case, these states are actually efficiently preparable. We can actually do, so we can potentially realize this task in an experiment, because these kinds of states are things that you can make with very low depth circuits. In any case, the complexity, the number of copies of the state that you require to determine the Pauli string, if you have access to a quantum memory, then it requires order n copies of the states to do so. But if you only have access to a classical memory, it's basically exponential in n up to log factors. There's a lower bound of exponential in n. So there's this exponential separation between being able to learn p, namely learning the p of the state in the context of a quantum memory versus a classical memory. And moreover, a variation of this task is actually gate efficient with the quantum memory, which resolves a conjecture that was put forth in this paper with Dorit and Xiaoyang. So now let me just show you for the moment some data from some forthcoming experiment that was done in collaboration with Google on their Sycamore processor. So what we do is we do a toy version of this experiment in which we have 21 qubits, which we have labeled here in blue, which correspond to the lab degrees of freedom. And then we have another 21 qubits in red, which correspond to the quantum memory. So the idea is that we are going to prepare, for example, this I plus P state on the system qubits, and then we can make various kinds of measurements and store them in the quantum memory. We can prepare more copies of the I plus P state and so on. And so we are basically letting half of the system act like the quantum memory and the other half of the system act like the lab. Now, we would like to then run this efficient quantum protocol, which determines essentially the value of the Pauli string. In fact, the actual thing that we run is a slightly more sophisticated variation of this. What we find is that we can, with the aid of the quantum memory, we can efficiently, as a function of system size, so this is the number of experiments, or rather the number of total measurements which are required. So this is log scale, that we can efficiently solve this Pauli distinction problem with the aid of these quantum memory registers. But if we don't have the aid of the quantum memory registers, if we only were able to do measurements on the blue registers, then we have a rigorous exponential lower bound. And if we try, for example, to instantiate the best algorithm that we can come up with without the aid of the quantum memory, then this task is rendered exponentially hard. So this is at least some kind of experimental confirmation or corroboration of this rigorous lower bound that we tried to prove, that we can do this efficient protocol with the aid of these additional quantum memory registers, but without them, the task is exponentially hard. So let me tell you some other results, and then we'll come back to some more experimental data, which is we can talk about shadow tomography without a quantum memory. So suppose we have a state rho, and we're given observables O1 through OM. We would like to determine all of the expectation values, trace of OI rho, to within some epsilon error. So a theorem that we were able to prove using these tree lower bound techniques is essentially that if you only have a classical memory, then you require the minimum of m, which is the number of observables, and 2 to the n over epsilon squared measurements. So this tells you basically how well you can perform this task of shadow tomography with a quantum memory. In fact, it's actually tight. It's upper and lower bounded up to logarithmic factors. So this, in other words, tells you essentially how efficient it is possible to perform this classical version of shadow tomography, or rather shadow tomography in the presence of a classical memory. This actually resolves an open problem that was posed by Scott Ahrens a few years ago. So now let me turn to some other kinds of problems, namely exponential separations and learning quantum channels. Let me give you first some intuition for a problem, and then I will explain what the problem is more specifically. Consider this thing that we call the fixed unitary problem, which is that it's difficult to distinguish between, you might expect intuitively that it's difficult to distinguish between time-independent evolution and time-dependent evolution if each is sufficiently chaotic. For example, suppose that you have random quantum circuit evolution, where maybe it's flow K evolution, where you evolve by the same fixed kind of chaotic circuit at each time step, versus if you evolve by a different circuit at each time step, which is sufficiently complicated. You might imagine that it's actually hard on the basis of making measurements of your system to determine whether your system is time dependent or time independent. And we're going to make this intuition precise by formulating a task. So the task is as follows. Suppose that we have a system for which the time evolution of the system either acts as the maximally depolarizing channel, namely completely depolarizes the system. So this would be like saying you act every single time that you're given a state, you act with a different IID Haar random unitary, for instance. Or by contrast, we evolve the system with a fixed Haar random unitary, namely we evolve by the same Haar random unitary each time. So this is like asking, is our dynamics completely depolarizing? Does it just completely depolarize the state to maximum mixed state? Or does it evolve it in a unitary way that's actually quite complicated because the unitary is Haar random? namely chosen uniformly at random from the hard distribution over the unitary ensemble, or over the unitary group. So by some combination of results, we can show that being able to distinguish between these two possibilities, namely the evolution, is efficient if you have access to a quantum memory, but it is inefficient if you do not have access to a quantum memory, if you only have access to a classical memory. Now, what's more interesting, and moreover, the protocol of the quantum memory is gate efficient. Now let me make an observation. In the setting where we've been talking about distinguishing between quantum states, we have been imagining that nature has been providing us with a state which we can then probe or measure. In the case where we want to distinguish between time evolutions or quantum channels more broadly, the setup is a little bit different. It's that we provide a state in the lab, and then we query nature to evolve the state. Namely, the coupling that nature provides is to evolve a state that we have initialized. And then we can, after we have evolved that state, we can then subsequently measure the evolved state and do what we wish with that information. So in this kind of problem, the thing that nature is providing is the time evolution, not the state. We provide the initial state. We also provide the basis in which we're going to measure the evolved state, but nature is just providing the time evolution. So now let's talk about a problem that is starting to crawl in the direction of more interesting, experimentally relevant, and maybe relevant for kind of interesting problems in condensed matter physics. We call this the symmetry distinction problem. And let me give you some intuition for this before stating the problem. So now you might have some intuition that it might be difficult a priori to determine the symmetry class of a strongly interacting quantum many-body system. And there's many different things you might mean by the symmetry class, but I'm going to take this to mean something quite narrow, which is that suppose that we consider let's recall the time reversal symmetry classes of unitaries. This is the Dyson classification, the threefold way classification of unitaries. So we can consider unitaries which are ordinary unitaries, which just their inverse is their dagger, their conjugate transpose. We can consider orthogonal matrices, which have the feature that their inverse is just their transpose. Or we can have symplectic matrices in which their symplectic transpose is equal to their inverse. And there is a way that I won't describe at the moment in which the orthogonal and symplectic classes realize different forms of time reversal symmetry, but let's not get into this at the moment. The task will simply be, suppose that our time evolution is either a Haar-random unitary or a Haar-random orthogonal matrix or a Haar-random symplectic matrix. And we would like to determine which of those three cases our evolution fits into. So that's the symmetry distinction problem. Suppose that nature provides us time evolution by either a fixed Haar-random unitary or a fixed Haar-random orthogonal matrix or a fixed Haar-random symplectic matrix, and we want to determine which of these three cases is being realized. So the result, quite interestingly, is that if you have access to a quantum memory, then you actually don't have to make very many measurements at all. You only have to essentially query nature to do an order one number of time evolutions to be able to determine which of these three cases we fit into. But if you only have access to a classical memory, then you require a lower bound of exponentially many measurements to determine which class of evolutions we fall into, either 1 or 2 or 3. Moreover, the protocol with the quantum memory is actually gate efficient. So this kind of experiment was realized in some toy example also on the Sycamore processor. So again, we think about these blue qubits as being ones which realize the lab system, and we think about the red qubits as those which realize the quantum memory. So the idea is that we can prepare some initial state of the qubits that are blue. We then evolve them by either a random quantum circuit that is built out of either unitaries or, on the other hand, of orthogonal matrices or symplectic matrices, for example. So these three different classes. And then what we can do is we can couple them to a quantum memory, and we can make joint measurements on the memory and on the system qubits, and we can use that to try to determine which symmetry class the evolution on the blue qubits has realized. So in other words, in this just case, there's going to be two cases. Either there's going to be a random quantum circuit built out of unitary gates, or a random quantum circuit that is built out of orthogonal gates. And our goal is to distinguish between the two cases. So the interesting thing is that if we only allow ourselves to make classical measurements on the blue system, then we prove that this, at least in the setting where our random quantum circuits are in fact extremely large depth, which is not what's going to be realized in this toy example on the quantum computer. But we might expect that it should be hard to distinguish between these kind of orthogonal class random quantum circuits and these unitary class random quantum circuits. And in fact, we can essentially show that if we have access to the quantum memory, then we can perform measurements in which the general versus orthogonal quantum circuits, the unitary versus orthogonal quantum circuits, will cluster out, namely just by making a certain class of joint measurements, which we run through some unsupervised learning protocol. That the basic point that you should take away from this is that if you have access to only these classical adaptive measurements, you can't tell the difference between these two symmetry classes. But if you have access to a quantum memory, there are protocols in which you can cluster instantiations of the protocol in which there was these unitary random quantum circuits versus these orthogonal quantum circuits. So let me now mention one final result, and then I will conclude and we can have further discussion, which is that I want to talk about another setting of exponential separation with a bounded quantum memory. And this is a particularly interesting result that is qualitatively and quantitatively different than the results that I have told you so far. So let me just alert you to the fact that it's a bit conceptually different, and I'll delineate the manner in which it is conceptually different. So we're going to consider shadow tomography with a bounded quantum memory. So what we're going to assume that we have a quantum memory, but now we're going to suppose that it's bounded in size. So in other words, previously we were not going to be so concerned with the size of our quantum memory, but now we're going to suppose that we only have access to k qubits of quantum memory. And we're going to understand how a certain task depends on how the difficulty of performing a certain task is going to depend on precisely the size of our quantum memory, on the bounded size of our quantum memory, namely k qubits. Okay, so let me read the statement of the theorem and then we can unpack it. So any learning algorithm with k qubits of quantum memory requires at least exponentially many in n minus k over 3 copies of rho to predict trace of p rho for all n qubit Pauli observables p with probability at least 2/3. Okay, so what does this mean? Consider the task if I give you a state rho and I say to you, I would like you to determine for every n qubit Pauli string p, the expectation value, in fact, just the absolute value of the expectation value of rho against p for all p. So there's exponentially many of these numbers, and I only care about what they are to within absolute value. And I ask, I want you to basically be able to succeed on this task with probability 2/3. I want you to get everything correct with probability 2/3. So I only ensure that I only require you to succeed on getting all of these, but only 2/3 of the time. Then the interesting thing is that if you only have access to k qubits of quantum memory, then this task is exponentially difficult to perform in the difference between n and k. In other words, if you have n qubits of quantum memory, this task is actually easy in terms of you don't require that many copies of rho to achieve the task. But if you have k, if the difference between n and k is parametrically large in n, then you require exponentially many copies. So notice that this lower bound is only polynomial when k scales like n minus some number times log of n. So the way you should interpret this result is that this is an example of a task, is that even when you have a quantum memory, it is difficult to perform the task unless your quantum memory is of size n. So that's quite interesting, because this is a completely unrestricted protocol. You can do any general quantum computation you want, but only with k qubits. And only with the state that you're provided and the additional k qubits of quantum memory. So there's no restriction on making classical measurements or anything like that. It can be purely quantum, but the boundedness of your quantum device is making the task exponentially hard unless your quantum device basically is essentially large enough, is essentially of size n, essentially parametrically. to perform the task. So this is quite an interesting result conceptually, because it's bounding the power. It's telling you that there is a bound on the power of full-fledged quantum computation, but for quantum computers of bounded size. So let me conclude with just a few comments, and then we can turn to questions. So the usual paradigm of quantum advantage is that typically we talk about how quantum computers are better than classical computers at classical problems. But something that I think is interesting in the context of these quantum memory type tasks is what we might call quantum memory advantage, which is that quantum memory has an advantage over classical memory for quantum experiments. Namely, that if we would like to perform some experiment in the lab, there might be a large advantage to having a quantum memory or a quantum computer that you can couple to your experimental apparatus that will improve your performance of the experiment. That the data in question that you are analyzing is not classical data. You're not trying to solve a classical problem, but you are trying to couple to a quantum system and trying to find information about a quantum system and are solving, in that sense, a quantum problem. So what we've done is we've developed a new framework for proving exponential separations between quantum learning algorithms with and without a quantum memory. We've established the first exponential trade-off between bounded quantum memory and query complexity. That was the last result that I told you about, where we bound the power of a quantum computer by virtue of its bounded size, even if you can do arbitrary quantum operations. We provided some experimental demonstration, a proof of concept of some kind of quantum memory advantage in the NISQ era. And a very crucial question, which we were forced to contend with if you want to scale these kinds of things up to larger system sizes, is what are the effects of noise? Do these exponential gaps evaporate in the presence of noise? Can we find versions of the tasks that I have told you which are more robust to noise? I think these are very interesting future questions. Also, you could ask, can we find other more physical examples along the lines of this I plus P task? In other words, can we find other examples which are experimentally realizable on NISQ devices? And maybe even more importantly, can we leverage any of the ideas here to determine experimental protocols which would be useful and valuable in contemporary experiments, for example, in the context of ultra-cold atom physics or condensed matter physics? In other words, can we go away from this realm of toy problems for which we can prove these exponential separations? Maybe we can find problems for which we can only prove polynomial separations, but they would actually be useful for contemporary experiments. That would be very interesting as well. Anyway, with that, thank you so much for your attention. I'm happy to answer any further questions that people have.
Well, thank you, Jordan, for really interesting and also provocative talk. I'm sure that it will entail a lot of discussion.
Great.
Yeah, how do I ask a
You
question?
already have a question, or Ed.
I'd like to ask a question.
Yeah.
Can I ask a question?
Yes.
Okay. Well, your model is that you're given things sequentially. But what if I told you, instead of that model, I just give you 2 copies at once, and then you have enough, your quantum computer is big enough to hold the 2 copies. Is that different than what you're doing?
Yeah, so that would be included in the setting that we're calling the quantum memory setting.
Yeah, so I mean, but you keep sort of insisting that you get one, you store it, and then you get another. But I could just give you 2 copies at once and have a big quantum computer that could handle it. It would be the same thing. Do you agree?
Yes. So that is, in other words, that's not, how do I say, that's allowed in the classical setting. Oh, sorry, that's allowed in this quantum memory setting, but we're not allowing that indeed in the classical setting. But one question.
Why?
Because it's a model for what people do in contemporary experiments, in the sense that, if you have, you have 1 copy of your experimental apparatus, like if you have the superconductor, which is in a certain state, it's not like you can, if you had 2 copies of the superconductor, then you could do something like that where you can make a joint measurement.
Right. You could just have 2 and then have enough room to entangle them, and that would be the same thing, right?
That's right. So we're trying to understand the difference between if you essentially only have 1 copy versus if you have these extra registers of quantum memory to play with.
Okay. May I ask another question? Or
Sure.
I'll be quiet. I don't want to dominate. So in the second Google example, where you talked about the symmetry properties, the state was a product state, right? Because you had these decoupled segments. And were the unitaries just acting on individual qubits, or were they connecting the qubits?
Oh, no, they were coupling the qubits.
They were?
Yeah.
But they were coupling them beyond the friend, They were going across the quantum computer?
Yeah, so for the I can go back, but let me just say it. So they're like brickwork random quantum circuits. So they're coupling nearest neighbors in a brickwork.
Oh, okay. So they go beyond the little connection you had in the middle.
That's right.
I don't think that was true in the other experiment, right? In the 1 plus epsilon experiment, I think it really is a product state. No.
Yeah. I mean, that's right. But in the other experiment, basically, we do nearest neighbor couplings, and we essentially do swaps to basically instantiate this brickwork circuit.
But the nearest neighbors were just between the blue and the red.
Oh no, there's also nearest neighbors between the blues and the blues.
You sure? Anyway, it's fine. It's fine. I'll be quiet. Yeah.
Sure. How do I say to evolve the random quantum circuit on top of the blue states, they are mutually coupled to each other, but to do a swap test between the reds and the blue, there's also a coupling between the reds and the blues.
Okay.
But maybe let me just mention one other thing, since you mentioned it before, this idea about replicas. Like, essentially if you have one replica of your system versus two replicas, and you can make these joint measurements. So let me mention one other result, which we were just able to prove in the last week, which pertains to that question, which maybe is relevant for this discussion. So essentially, you could regard the kinds of results that I've told you about, at least in the way that you have phrased it, is an advantage to being able to make quantum measurements on one replica versus two replicas. Mm-hmm. So one thing that you can ask is there any, so in other words, we found tasks which are exponentially inefficient if you only have one replica, which are efficient if you have two replicas. You might ask, are there any quantum tasks which are exponentially hard if you have k replicas, but are easy if you have more than k replicas? Okay. So in other words, we've sort of dealt with the k equals 1 version of this. Can you do this for arbitrary k? It turns out that there is a hierarchy of tasks which can be written down rather explicitly, for which there is a separation between what you can do with k replicas and more than k replicas. There's an exponential separation. I just wanted to mention that, since that might be of interest.
Let me just say one more thing. That was a great talk.
Yeah.
Thank you. I really liked it.
Arthur, do you have a question?
Yeah, I think I missed something very important towards the first half of your talk, which was, if I was doing this all classically and I just had some agent who was, receiving these states, making these measurements, then they could probably use some algorithm like, maximizing information gain to choose what measurement they should make next and subsequently on future measurements. What's the difference? What's the key idea? What's the key difference between if you use this quantum memory instead? How would the algorithm change?
Well, it's related to also what Eddie was saying. So you can say it this way, is that the ability to be able to access multiple copies of the state simultaneously and to make joint measurements on multiple copies of the states is what confers the quantum advantage. So for example, let's consider the setting where I'm giving you a Haar random pure state versus a maximally mixed state. I may have said this in passing, but I may have said it a little too quickly, which is that if I give you 2 copies of a pure state versus, say, 2 copies of a maximally mixed state, it's easy to figure out which is which because you do a swap test. You measure the swap operator on rho tensor rho, and you basically, the outcome is trace of rho squared, which is 1 if your state is pure, and then 1 over d, 1 over the dimension if your state is the maximally mixed state. The thing which this is getting at is that if you only have access to 1 copy of the state at a time, then you can't do something like that. And in fact, it's exponentially hard regardless of what you do, even if you work adaptively in order to distinguish between the maximally mixed setting and the Haar random pure setting. So that's the intuition. It's the ability to make joint measurements on multiple replicas simultaneously is what the quantum memory is providing you with. And in the very last thing that I told you about, like in the talk, this bounded quantum memory result, it's like a more refined version of that, because it's saying that if I give you extra qubits, but not enough to do something like a swap test, then it's still actually kind of exponentially hard. That's the thing which is conceptually interesting about that, is that even if I give you just shy of the number of qubits you would need to do a swap test, it's still not going to cut it.
I see. Perfect. Thank you.
Sure. Thanks.
So are there other questions?
You has a question.
Oh.
Hi, you.
Yeah. Hi. Hi, Jordan. My question is that considering the to extend to KD equal to 1 K or general K is maybe the task to estimate trace rho power of K, is that kind of task similar to the purity?
So I can mention kind of what that task is. So the problem about estimating trace of road to decay is that if your state is, say, very impure, like a maximum mixed state, then that trace of road to decay will be like, exponentially small in D, be like 1/. So that you don't want to do. That's going to be really tricky. Essentially, what you do is that you prepare the states that you would like to distinguish, for example. So we talked about these I plus P states, I plus identity plus Pauli over D. Okay, those were states that entered into this talk. Instead of having a Pauli operator, what you do is that you take a Pauli operator and you conjugate it by a unitary 2K design, which you can, or an epsilon approximate unitary 2K design, which you can realize by a quantum circuit of polynomial depth. And those families of states are basically hard to distinguish from one another when you only have K copies. But if you have more than K copies, loosely speaking, you can actually distinguish them from one another. You leverage the property of epsilon approximate K designs and some of this learning tree technology to be able to show that if you have K replicas simultaneously, you still will not be able to make joint measurements, which will kind of determine that, which will distinguish between anything in that class of states. That's roughly the idea.
Yeah. Thanks for your, thanks for.
You have another question, Arthur. Yeah, sorry. The answer to this question may even be contained in the previous answer. But what if I have no idea what state I'm working with? Like, I'm not trying to distinguish between two. I'm just trying to discover one, and it could be one of an infinitude, right? Like on any mixed state, or let's just say even any pure state. Do you still get an advantage in this case? Or is this advantage specifically for the case if I'm trying to distinguish like a finite collection of states? Yeah, so there are examples of problems. And okay, so an example of a problem of the kind that you described would just be like quantum tomography of like, given an unknown state, determine the parameters of that state. And let me just make a comment about that. Of course, in the worst case, it's if you work adaptive, if you have access to many replicas versus if you have access to one copy at a time, well, they're both exponential, but there's there's some exponential separation, or believe that there's some exponential separation between them. But I don't think that we actually really know exactly where the adaptive version of tomography lies. I think that that's still kind of open, exactly like if you could do adaptive sequential tomography, what is the query complexity of that relative to sequential but non-adaptive versus having access to all of the copies simultaneously. But in general, the problems that I told you, you're quite right. We're distinguishing between some discrete family of states, or rather between two classes of states, which maybe each be continuous, but there is only a discrete number of classes. And indeed, there are other variations of these tasks that can be continuous families, and I could give some examples. But I just mean that if it's somehow too general, then you're going to end up doing something like a tomography task for which there's other techniques and other literature to deal with that. Awesome. Thank you so much. Sure.
So thank you, Jordan, for a really interesting talk and very provocative. It raised a lot of discussion, and we'll look forward to interaction with you in person, and see everybody next week. Bye-bye.
Sounds good. Thanks again for having me. Take care.
Bye-bye.
Bye.